Okay, it's been some time. What's this video about? These are my notes on modern robotics, the first chapter only. So it's mostly about the representation of a rigid body as seen from some other frame uh, in 3D space. Right. So let's go with some terminology. A frame is basically the ordered list of basis vectors that may be attached to a body, making it a body frame. So a frame doesn't have to be attached to a body. We can position a frame anywhere, but most of the times it's attached to a body because that way it's useful. Okay. When we refer to a body frame, we mean a motionless frame that is instantaneously coincident with the frame that is fixed to a possibly moving body. So for example, if you have a block, uh, right, so it should be in 3D, and this block is moving like that, right? So at some certain some certain time, you will just take this frame, right? You will just make this origin and figure out the basis vectors, and that's your frame. Now after some point, the block would have moved forward, right? So now it has moved forward, maybe somewhere over here like this, but the frame hasn't moved. So that's what we mean when we say that the frames are motionless, and they may be formed because of a moving body, but they themselves are not moving, right? So that would mean that you can actually have things like the velocity of this body. Let's call this body as, I don't know, capital B. So the velocity of body B as seen from this frame, let's call this frame the frame B. So this would be written as v vector of B with respect to B. It should be like this, I guess, BB. All right, cool. Or you could view the frame itself as moving, right? But whenever we'll be talking about measuring something with respect, measuring a velocity basically with respect to some other frame, that basically means that the frame that we're using to measure something, that is stationary. So when we say the velocity of a frame, B with respect to the space frame S, here the space frame S is stationary, and by velocity we mean how is this frame changing over time, right? So how is this origin changing over time if it is if like it's being updated as this body moves. Does that make sense? All right. So that's good and all, fine. A vector can, so this is just basic linear algebra, you don't have to look at this. So first we define a vector, which I'm writing like this. So for like telling you what matrices actually do, what I'm doing is that I'm writing a vector like this. So it's the dot product between this vector, which contains the basis vectors. I know it's a weird concept, but trust me, it's a lot better to understand this and then to go to matrices instead of understanding matrices and then to go to this. So yeah, when we say like some vector is equal to 2i hat plus 3j hat plus 5k hat, we could also think of it as something like this: a vector containing i hat, j hat, k hat, that dotted with 2, 3, 5. So when I say that this is a vector, what I should have said is that this is an array. So it's an array of objects, I would say, and the dot product, that's defined by just, you know, multiplying the corresponding elements and adding them up. All right, nothing too fancy till now. And now this thing can be also written like this: I hat, j hat, k hat, and 2, 3, 5. Right? So here comes a bit of matrix multiplication. So you have to understand how to multiply these two matrices, and what does this actually mean. It just means that you're doing 2i hat plus 3j hat plus 5k hat, right? So this goes here, this goes there, that goes there. Nothing complicated. All right. So rotation matrices can be used to describe the orientation of a body with respect to another. The basis vectors of that frame, as expressed in observer's frame coordinate, the observer frame's coordinate system, form the columns of the rotation matrix. So that's basically getting into what a matrix actually does, right? So instead of writing just I hat, j hat, k hat, if say your I hat can be written as, I don't know, let's just say like x hat plus y hat. where x hat and y hat are not I hat and j hat. So there's some frame with basis vectors I hat, j hat, k hat, and there's some other frame with basis vectors x hat, y hat, and z hat, right? Then writing these as seen from this frame, that will be done like this: I hat equal to x hat plus y hat. Just an example, it's not really like that. Then j hat might be, I don't know, y hat minus k minus z hat, something like that. Then what that means is you can write I hat as this thing. You can write it like this: x hat, y hat, x hat, y hat, z hat, and this times this vector, which is just 1 1 0, right? Using the kind of dot product thing that we defined earlier, right? So using this definition of multiplication of these two arrays, basically you can write it like that. So you can do it for I hat, j hat, k hat, right? And then pull out this vector. I know it's a lot of abuse of notation, but come on, it will be useful. So you can just pull out this vector, and then the thing that you get over here is 1 1 0, whatever j hat is. In this case it was 0 1 negative 1. Whatever k hat was, I don't know, this is 0 0 0, could be anything. Or let's not go with 0 0 0, let's just go with 0 0 1 or something like that. And then this thing 2 3 5, and you pulled out this thing, so now it's this thing: x hat, y hat, z hat. So this basically, yeah, once you do this multiplication, the vector that you will get, that will be the coordinates of the vector that was being represented by 2 3 5 in this frame, the coordinates of that vector in this frame, right? So that's what this matrix actually does. And yeah, let's move on. So for this complete section, we are actually using the boldface v and v vector as different things. So v vector is a physical concept, and v is just an array of numbers, right? So as I said, first one is an array of numbers, second is a physical vector, but soon we'll be using this interchangeably because of course we are more familiar with the vector notation rather than this boldface notation that's mainly used for matrices. I mean, I use that for matrices. Okay, such matrices give us a way to find the representation of a vector in a frame based on the representation in a different frame. So yeah, the exact same thing that I did over here. Okay, so now we're getting to rotation matrices. Like, how do rotation matrices work? So let's go to a 2D case first. In 2D, a rotation matrix which rotates some vector by angle theta, that's given by this thing. So what do I mean when I say it rotates by theta? So a matrix isn't just a way of representation of a frame with respect to another, it is also a function. So applying this function on this, that does some certain operation, which there's no name for this operation right now. Anyway, you can also view a matrix as a function, and you can also view the matrix as a representation. All right, so we'll have to get comfortable interchanging between these two interpretations of a matrix. Fine. So the columns of rotation matrix are, so the rotation matrix in 2D, that's somewhat like this. So a complex number is a better way to actually rotate vectors in 2D, and I'm gonna use Euler's theorem in complex numbers to actually figure out what this matrix should be. So yeah, let's do it like this. Say x hat plus I y hat is the rotated vector, and initially just x plus I y, that was the to be rotated vector. Way you rotate is basically just multiply by a complex number e power I theta that rotates anti-clockwise by theta. You all know that, right? This is basically what cosine theta plus I sine theta, and that times x plus I y. Yeah, using Euler's theorem. You might be thinking, why am I using all this instead of normal trigonometry? Because I don't want to do it in multiple quadrants and prove a lot of weird like cases, so I'm just gonna do it like this. So this is its real part, it will just be cosine theta, x cosine theta minus y sine theta, and its imaginary part will just be y cosine theta plus x sine theta, right? So now if I convert this to vector notation, it's like this: x hat y hat, that's equal to so x cosine theta minus y sine theta And over here you got x sine theta plus y cosine theta. Now this thing is the same as saying cosine theta, negative sine theta, cosine theta. This matrix applied on xy. Pretty basic actually. So if you're not comfortable with all of this, you should probably watch some linear algebra course, and there they will introduce you to all of these things. So yeah, this is our rotation matrix. This is what it looks like in 2D. How many degrees of freedom are there for this matrix? That is, in how many variables is this a function, right? Because matrix by itself is also an object which depends on the variable theta, of course. What else does it depend on? Well, it only depends on one thing, right? Theta is the only variable, but that's not the case for 3D matrices. They depend on, I guess they depend on 3 variables, right? I'll explain what those variables are, but for now, let's just focus on the 2D matrices. Those depend on a single variable. Why is that the case? Why could we write everything using theta? Well, you might say, okay, we just want to rotate by angle theta, right? That's why it's a single variable. But this matrix actually has 4 entries, and these 4 entries could be different. So why not 4 variables? Why is it a single variable? That's because there are restrictions. So let's just say that the matrix was A, B, C, D. The first restriction is that the matrix should be orthogonal. That is that, how do you even say this? So I'll have to introduce you to orthogonal matrices in that case. But yeah, rotation matrix is orthogonal, which means that its column vectors, those are unit vectors, and those are perpendicular to each other. So that actually creates how many, like 3 equations. So first equation is a square plus b square equal to 0. Second is that c square plus d square equal to 0, and last equation is that ac plus bd that's equal to 0, right? So yeah, there will be those many those many equations created, and every single equation which is new, that is it can't be constructed from the already existing equations, that eliminates one variable, right? So what that means is the 3 equations eliminate 3 variables, so there's only a single variable that's going to describe everything, and that's how we get the degrees of freedom of a matrix. And this also basically tells you that this is how we get the degrees of freedom of a body, because a matrix can also represent a body. It's not just a function, it's also a representation of the basis vectors of some certain body, right? Or some certain frame or whatever. So yeah, that frame or that body has degrees of freedom given by number of variables that describe the matrix. In this case, it's just a single variable, so there is 1 degree of freedom. And yeah, of course it's 2 because the vectors themselves have to be unit vectors, and 2 times 2 minus 1 upon 2 because the dot products have to be 0. Alright, and similarly a 3D rotation matrix that will have 3 variables. It may be 3 angles, Eulerian angles, or Euler angles, I don't know what it's called. A unit vector, 2 variables, and an angle, or any other thing, right? Rotation matrices aren't just objects to represent function, but also okay. I mean, we already did that. All right. So this is a 2D rotation matrix, and this is boldface v s dash equal to whatever. With some abuse of notations for the S frame, we can write this thing. So it doesn't have to be necessarily for the S frame, because as you will see later on, we'll be using this notation for any frame. And this is also not abuse of notation actually, because this is legit. Alright, so v vector as a physical quantity as well, you can kind of put that as an input to a matrix, right? It's not a bad thing to do, and we already did that, right? Yeah, we did that somewhere already. I don't remember where we did that. Anyway, so you can do that. So it's not exactly abuse of notation. So I should probably delete this thing, or we can write this. Okay, now let's consider a point with position RT. Oh, so this is getting into the it's getting into the rotation matrix derivation stuff. Fine, so we are doing it for 3D, I guess. Okay, so now we are doing it for 3D. So now let's consider a point with position vector RT. fixed to a rotating rigid body with frame B attached to it. So when I say attached to it, what I actually mean is that you have to stop time, you have to separate the frame from the body and then let the body continue, right? So that you get like an instance of that frame. Does that make sense? Maybe it's just like it's hard to explain what exactly the frame actually is, but yeah, it's basically attached to it. So as time moves on, the instance of this frame that gets updated, right? Okay, so yeah, let's consider a point with position vector rt fixed to a rotating rigid body with frame b attached to it. In that frame, coordinates of the point aren't changing. They are always equal to this, or with abuse of notation this. Thus we can write all that. Okay, let's say that the body is rotating and not translating in any way with angular velocity omega equal to d theta upon dt over an axis to the origin along the unit vector omega hat in the right-handed manner. Yeah, so it's not translating, so its origin, the origin of the frame B, that's coinciding with the origin of S. Yeah, I should have said that earlier, but yeah, that's how it is. So you can write the position, I shouldn't say the position, well, okay, it's actually a point with position vector, fine, and that's fixed to rectangular one. Yeah, so this R thing is the position of that point, and the rigid body itself is actually rotating with the origins of the frame B and the frame S coincident, right? Frame S is the space frame, okay, or I could say the ground frame or whatever. Yeah, and our goal is to figure out this matrix R. So we have this R vector as a function of time being given as this rotation matrix as a function of time applied on its initial value, right? Okay, or you could write this as well, fine. And let's just read that one once again. So there's a mention about this vector over here, yeah, omega vector. So what's happening is something like this. You have this frame S with our normal xyz coordinates. This is the rigid body we are talking about. It's rotating about this vector omega hat with angular velocity omega, of course, right? Yeah, and R is a point on this rotating rigid body. So of course, with respect to what do I say? Okay, with respect to this body itself, or the frame attached to the body, right, this guy's coordinates are constant, right? Yeah, but with respect to this frame, this guy's coordinates, those are not constant, those change. Now how do they change? They change by the rotation matrix. So I mean, we already said that the matrix is representing the basis vectors of this body with respect to this frame. That will be a rotation matrix, which is also kind of like a function. Yeah, I should have, yeah, there was that thing as well, the subscript cancellation rule, which I guess I didn't write, but anyway. Oh yeah, okay, this thing. So VA equal to RAB VB. So just as I did, we can write X A Y A Z A as its as the representation in some other frame, right? And then we can multiply this matrix with this vector to get the coordinates in that other frame, right? So the matrix is called RAB if you are describing the frame B's basis vectors in A, right? Yeah, and then of course this matrix applied on the coordinates of some certain vector in B, right? That would be the coordinates of that same vector in A, and AB are frames, of course, right? So in this case, since we want the coordinates of this thing in S, so this thing in S, and it's a function of t, of course, which we'll do that later. This would be, so it's the matrix representing the basis vectors of our frame B in S times the coordinates of this thing in B, which we know is just R naught. right? And at this point, let's just use the boldface notation because we're dealing with coordinates. Yeah, all right then. So that's what this equation is. And of course, these are functions of time. So this is a function of time, and this is also a function of time. This is not a function of time. It doesn't change. Or you can write this as well. Okay. Now, since it's moving with omega, the derivative of this position that can be given by some physics basically. But all in all, it's just a derivative of this matrix times this vector, right? Because the vector is not actually changing. So r naught, it does not change, but this matrix does. Okay, so let's say the body is rotating and not translating anyway with an angular velocity omega equal. We already did that, sorry. We already read all that. So this is the thing. Okay, so the velocity of the body as seen from the space frame, that's equal to dr upon dt. That's this thing, but we know that v vector can be given as omega cross r, right? You know, the usual physics, rigid body dynamics stuff. You already know that. I guess you already know that. I'm assuming you already know that. If you don't understand why this happens, I don't know, look at some physics videos. Yeah, so v vector equal to omega vector cross r vector, where omega vector is omega times omega hat. Of course, this thing is just over omega vector. So this is our v vector, something like that. Okay. So if we substitute that in this equation, what you get is omega omega hat cross r vector, that's equal to this times omega r naught, right? Because there's a d theta upon dt over there. So actually I changed the thing. So d upon dt, instead of that I'm using d upon d theta, and that times of d theta upon dt. So the chain rule. Yeah, and that d theta upon dt is just omega. So these two omega, they get cancelled. So what you get is like omega hat cross r vector, that's equal to d upon d theta r times r naught. So now this actually works for any r naught that you take on this body. What that means is like this is actually general equation that actually means like this operation of cross multiplying with omega hat, that's the same thing as multiplying this matrix. So now here's gonna be something crazy. We actually write this operation as a matrix itself. So say you want to take a cross product with some certain vector, you can think of the that operation itself as a matrix, which, I mean, you can look that up, right? It also has a name, but yeah, just you know, search cross product as a matrix and you'll probably find the thing. I've used that in my videos before, so one way I had to find the inertia tensor. Anyway, so I'm assuming you already know that and you are up to date. Fine. So then we can use that matrix over here, and what we basically get is that d upon d theta of r, that's equal to this times this thing. Yeah. Oh yeah, you also have to actually replace r vector by this thing, because the r naughts, those have to be the same. You can't just say like this is equal to that, because r vector and r naught vector are different vectors. So replace r by this thing, and now you can cancel these r naught vectors. So now you can say, okay, d upon d theta of r, the capital R of course, that's equal to omega cross capital R, and this differential equation will be very useful later on. Okay, so first a nice property of this omega cross thing. So it has the property that its cube is equal to negative omega cross. So it's somewhat like, how would I say, it's somewhat like iota square equal to -1, but not quite, because first you have to take the cross product with omega itself, which, so for some certain vector, just say this vector is, I don't know, v vector, fine. I know it's different, but whatever. Or let's use p vector instead, or p hat vector. Okay, p hat cross, right, that operation. So first you have to take the cross product with p hat. This will be the same thing as taking the cross product with this vector, which is not having any component in the p hat direction, right? So you can just forget about this vector completely. It's the same thing as taking this thing. Once you do that, you rotate it by 90 degree in this plane, right? And then once you do it again, you rotate it over here. So this is like p hat cross squared times v vector. Now as you can see, this is negative of this vector, right? Its projection on this plane, but it's not equal to the vector, okay, negative of the vector itself. So that's why you have to do this 3 times, so that you can actually say that, okay, p p vector cross that thing cubed p vector, that's actually equal to negative of something, and that's negative of this vector, which is just p hat cross v vector, right? And that's how you get this property. It's very intuitive, in fact. Okay. Yeah, and now we can finally delete these are not vectors, because those are general vectors, not some specific vectors for which this is going to work. What that means is you can actually have this differential equation, and the way to solve this differential equation, emphasis on solve, we are basically just guessing a solution. Yeah, really, we're just guessing a solution. So usually if you had a differential equation, say d upon dt x equal to, I don't know, a times x, then what you would say is like x is equal to a e power t, or okay, sorry, a e power at, right? Yeah, that would be our guess. But here, can you do the same? Can you actually say that r is equal to r naught e power, so this would be our a, or you could just say x equal to x naught e power at. Can you do the same thing over here? So what we are attempting to do is r equal to r naught e power, our a is this thing omega cross, and our instead of t we have theta, so this thing. Does this actually make any sense? It does. You should watch the 3 blue 1 brown video on why raising e to a matrix actually makes sense. So this is defined using the exponential function, and once you use the exponential function and you do some Taylor expansion and some other stuff, pretty much the same kind of thing that you do for getting the Euler's theorem. So once you do all that, you'll end up with this. So this exponential is equal to the identity matrix plus sine theta omega cross, then 1 minus cosine theta, this matrix squared, right, using this property. So yeah, that's why I said it's like iota square equal to -1, but not quite. That's why you have 3 terms instead of just 2. So if this was actually just -1 or negative identity matrix, what would actually happen is that, like, the 1 minus cosine theta, negative of that, just be negative identity matrix, this would cancel with that, and you would have positive cosine theta. So this would basically become like cosine theta plus I sine theta, something like that, just with I replaced by this matrix. But yeah, this is not equal to negative identity matrix, okay? Just keep that in mind. Fine. So we have this thing. Also, there's an important thing, that this R naught, it is actually the same thing as the identity matrix, because here we had the restriction that the origins must be coincident, right? And we also will put an extra restriction that the basis vectors must also be coincident. Now you might be thinking, why do we have to do that? Just to make it like look better, basically. So we want to think of this as something that we will apply on other matrices. So it should be something like a function. It shouldn't be just a representation, right? So that's why I'm just thinking of the rotation itself. I'm not thinking of what's happening to this frame, right? So just to think of the rotation itself, I'm thinking the frame was initially coincident with our space frame. And so because that's the case, our R naught is just the same thing as the identity matrix. So the matrix representing a rotation about this vector by angle theta of a certain frame or some certain vector. I shouldn't say certain frame, actually, that's kind of not correct, but yeah, it does it rotates the basis vectors by in that way, right? So it does actually represent the rotation of the whole frame itself. So if you're not getting why I'm saying that it does, I mean, you already are, I guess, sure that the rotation matrix applied on some vector gives a rotated vector, right? But what would happen if you apply the rotation matrix on a set of vectors, or should I say an array of vectors? So like v1 vector, v2 vector, v3 vector. The way that matrix multiplication works is that you just apply this matrix on the column vectors of this matrix, right? And you put that in a new matrix, right, in that order. So this is actually the same thing as this matrix, rv1 plus, I should say plus, I can't use comma over here because that's not usual notation, but whatever, just comma rv2 vector and comma rv3 vector. So this matrix, clearly it's a matrix, right? Just remove the comma, put white space between, whatever, you get the thing, right? So this is a matrix basically. uh, so it's equal to that. So like this is the same thing as just v1 vector dash and v2 vector dash and v3 vector dash. So the rotated vectors, right, the matrix formed by that. So in a sense it has rotated the whole frame itself in the way that we want it to do, right, about omega vector by angle theta. Okay, that's awesome. So now we have a way to calculate a rotation matrix in 3D. Awesome. But what if you were given a rotation matrix and then you also, actually before that, here's a more believable way to figure out the same thing. So, you can like take some projections and do some cross product stuff, and yeah, you will eventually end up with the same thing. Just read it. I'm not gonna narrate it to you. Fine. Okay, and so how to get the rotation matrix given omega vector and given theta, but how would you do the opposite? So we are getting into the territory of taking the natural log of a matrix, because we have the rotation matrix being given by e power omega cross theta. So we want to figure out what this will be. To do that, you of course have to take natural log of that. But how do we do that? How do we actually figure out what this is going to be, like what this is and what that is given our rotation matrix? It's not an actual operation, it's more like a procedure. So the way to do that is by using these two equations. The trace of r, that's equal to 1 plus 2 cosine theta. So now you know what theta is. Awesome. But how do you get omega? So since the rotation matrix, the inverse of that is just r of negative theta, and because it's an orthogonal matrix, it's also the transpose of the matrix itself. So we have r transpose equal to r of negative theta. But r of negative theta, if we put that in the original equation we used to calculate the matrix, so in this equation you'll just get this expression, right? So adding this, or I should say subtracting this from that actually gives us 2 sine theta omega cross. So all we have to do is just transpose the matrix, subtract the transpose from the original matrix, and you get 2 sine theta omega cross. If this is the 0 matrix, then well, that's nice, sine theta was 0. If it's not, then since we already figured out what the value of theta is going to be, you can divide by 2 sine theta to get omega cross. And there you go. And okay, if theta equal to n pi, then this thing will be equal to 0, so like r equal to r transpose. Yeah, and actually putting that into the final expression we get for the rotation matrix, you'll just have this thing. So that's like omega I, which is, so it's like omega x, omega y, omega z, something like that. That's equal to this, so you get the expression. I mean, this is a very special case, we won't be using this all the time, but yeah. So whenever theta equal to n pi for odd n. So what's the difference, odd n and yeah, so like odd n and even n? What would be the thing for even n? Well, for even n, just think about it, what's gonna happen. So if it's like 2n pi, that's actually taking a full circle rotation about the axis. So it turns the vector into itself. So it's the same thing as the identity matrix. So it doesn't make sense to take the natural log of that, because like we understand the matrix very well. We don't have to figure out what's the axis, how much, because this identity matrix could be like it. How do I say this? So if you have some certain axis omega 1 and you rotate 2 pi about that, this operation is the identity matrix, but this is also the same thing as this operation omega 2, and you rotate 2 pi about that, right? So both of these actually give the identity matrix. So which of the omega vectors should we choose, right? So it doesn't make sense. So yeah, the natural log of identity matrix is not defined. That's what it is. So it has to be an odd number. So if it's an odd number, then basically you're just doing the opposite of this vector, because rotating by pi or 3 pi or so on about some axis, right? So yeah, you're just doing negative of the thing. I wouldn't say exactly negative. Yeah, it's not exactly like that. because if this has some component along the axis, actually does this thing, right? This is what pi would do. So it's not just the negative of that. Fine. So theta equal to n pi, it's this thing. So it's almost the negative identity matrix, but not quite, because you have these terms 2 omega 1 square, 2 omega 1, omega 2, so on. So these would be 0 if the, how do I even say this? So like if these would be 0, then it would be negative identity matrix, but no, there's some extra stuff over there. So yeah. Okay, so now we covered all the cases how to get omega and theta given the rotation matrix. Let's go to the next part. 2D rigid body translation as 3D share. So we already figured out what rotation is, how it works. What about translation? So first let's go to the 2D case. Say you have xy as your original thing and you want to get x hat sorry for that. You want to get x dash y dash, which is the translated vector. So you translate by AB. The usual way to do that is just this thing. You add these two vectors, but there's a better way to do that, which is, I wouldn't say better, but a way that involves matrices. And how do I even say this? That's more formal. So say you want to, like, code a program that will translate and rotate vectors, right? And you want to be able to do that using just matrices, right? Just by applying matrices. What you should be doing is you should be creating a 3x3 matrix to represent translation in the 2D case. So that in that way you can also represent a rotation and translation in the same matrix. You will see what I mean later, but just think of it as an extra way of representing translation for now. We can also write it like this. So you have x hat y, okay, x dash y dash 1 equal to this is the 2x2 identity matrix. You got a, b, and 1 over here, and x, y, 1. So what's this 1 for? What's this 1 for? What's this 1 for? Why are there zeros here? Well, actually try multiplying the thing. So first we just put this x, y thing in this 2x2 identity matrix, right? Because it's not having any rotation thing. Then this 1 will go to the last column. You will add a, b, and 1, right? That's how you get this thing. Yeah, I guess that was the thing. So there's supposed to be 0 over there, 0 over there, and there's supposed to be 1 over there. Oh yeah, and why was there so the 1 is involved there because we want transformation matrices to be having closure, so that a transformation matrix applied on another transformation matrix applied on some vector, right, that doesn't mess things up. Because if you have the transformation matrix having all 0 in the last entries, so if you have something like this 1 1 0 0 0 0 0 a b x y 1, I mean, yeah, I get it. It actually does give us, this is like, okay, x dash y dash 0 is equal to this thing and stuff. I get it. You can of course do that, but then if you want to apply another matrix on this is 0. It's not 1 anymore, so it will be bad. So you have to have 1 over there, and the way to do that is to have 1 over here, right? So the general form of doing that is something like this. You have the identity matrix in 2x2 that is here. Then you have this 0. So okay, this is kind of weird. You might not be able to understand this notation directly, but think about it. What's happening over here is that this is the I2 we are referring to, and this 0 is actually 2 zeros. So this 0 and that 0, both of them, we're thinking of them as just an array of zeros. Think of it like that. So yeah, and this 1 is this 1, of course, and p vector is ab. So you have condensed everything in this notation, and xy is r vector and 1 over there. You'll have to get familiar with the elements of a matrix being big matrices themselves. Yeah, you just have to get familiar with that. Just think about what's happening here, what this notation means, and then yeah, this is the nicest way to represent translation. So now you're thinking, okay, there's I2 over there. What would happen if we put something else? So for example, if we put a rotation matrix over there, what would happen? That would first of all rotate our vector, and then it would add p vector to it. So that's why we use these kind of matrices, because then you can represent rotation and translation simultaneously. Okay. So now there are a bit more. Yes, there are some more tidbits over here. The matrix on RHS of this text, RHS is a shear matrix that transform. Oh, this text, fine. This text RHS. So this matrix, this is a shear matrix that translates the vector xyz by zp hat. Zp vector. Right? We use the plane z equal to 1 as the 2D space where original 2D vectors live. So if this was not 1, if this was z, right, then you would get like x dash y dash z dash equal to all this matrix applied on x y z. So you just have z times this vector, right? So then our r dash vector over here, that would not be r vector plus p vector, that would actually be r vector plus z times p vector. So that's why it's a shear, right? Yeah. So if z was 0, this would be just r vector, which means in the xy plane there's no shear. If z equal to 1, then it would be r vector plus p vector. So there's a shear, or like, yeah, what's basically happening is that you have the xyz space. For the z equal to 1, you're like moving this whole plane itself by some certain amount, and for z equal to 2, you're moving it by twice that amount. I should say twice the vector. For the actual xy plane, you're not moving it at all. So this is z equal to 0, z equal to 1, z equal to 2, and this is like 1p vector, 2p vectors, 3p vectors eventually when at z equal to 3, and so on. So yeah, this is basically a shear, right? Okay. Okay, so this matrix represents a shear, but this won't be the case when you replace I2 by some rotation matrix. At that point, this does not, of course, represent shear. It represents something more than that. It represents a rotation and then shearing. Okay. Yeah. So usually, you would have to do this to represent rotation and translation, but now you can just do this, right? So why are we doing this? Why are we thinking of it in a like a single object? Because as it turns out, you will have a nice formula to figure out these kind of objects once we are done with the whole derivation. So for now, just think of it as another way. So okay, it's not hard to guess the next step. Yeah, we are going to 3D now. So instead of having I2, we are going to I3 and R in 3D vectors, right? So thing is pretty much still the same kind of notation, except this RAB is now a 3 by 3 matrix, and there will be 3 zeros over here, and this will be 3. This will be a 3 vector. Okay. So this will of course work on 4 vectors. I mean, when I say 4 vectors, I mean like, okay, vectors, 4D vectors. That's what I should have said. So it will work on 4D vectors. For example, this was a 3D vector, and this was a 3 by 3 matrix. It was working on a 3D vector. Similarly, this will work on a 4D vector. But if you want this to work on a 3D vector, what we can do is like we can define this multiplication separately, right? It won't be matrix multiplication, but you can apply this apply this function on a 3D vector as well. Similarly, you can do it for the 2D case as well. Okay, so we'll do it like this. The matrix T, which is what we're calling all of this, applied on R vector means R vector plus P vector when the R vector is 3D, and the R vector 1, this thing would be 4D in that case. Okay, all right. So this is good and all, but what else can it do? So this matrix can also represent the position as well as the orientation of some rigid body as viewed from some frame, right? And then you can actually translate into different frames to view the rigid body. So I'll explain. As you already know that the rotation matrix is able to represent the orientation of the the basis vector thing, right? The orientation of the frame of the rigid body as viewed from some other frame. This p vector, when we are including that as well, now it represents the position as well. All right, but because these kind of matrices, which are called transformation matrices, have closure, that is, when you do this thing r a b p a b, so p vector a b is just, you know, the origin of the frame b, its position vector in frame a. All right, so if you do this thing r a b p a b 1, this times r b c p b c 1, and you carry out the multiplication as normal matrices, you actually will get this thing. So you should like verify it yourself. Now, although the multiplication is, I mean, it makes sense if this was, if these actually were numbers, but considering that these are actually matrices and not numbers, this thing, this equation can look dubious, and it should. So just, you know, get used to it. Think about all the, you know, like all the actual things happening inside the multiplication and how they relate to these multiplications, right? And you'll get used to it, I'm sure of it. Yeah, you can visualize that thing happening. So like all of these columns going into this bigger matrix, right? The first column goes like this, so the first three entries go, those go like this, and this is the 0th entry, so that goes over there, which means like, yeah, all of that will be gone. And so it's like these three entries actually go into this matrix, I should say, right? Similarly for the second column, third column as well. So now by this point, all of this has gone into that matrix. So this is just basically like just the multiplication of this and that. That's how we do that. And for the last column, this just goes like that. So it basically, you know, these first three entries go into this. Wait, is my pointer actually on this? Okay, maybe my pointer is not on the screen. Anyway, then this wouldn't make sense what I was saying right now. Anyway, yeah. So yeah, just figure it out. That's all I can say right now. But yes, this actually works. Try it out. Like, try some examples first, and this won't look that dubious afterwards. Okay, so TAB, TBC, this is actually equal to TAC. So there's a subscript cancellation rule that you can use. So you can cancel these two B's and it will just become TAC, right? Just a mnemonic to, you know, remember what actually happens when you multiply these kind of matrices. But what that means is like the representation of the frame C in B, that multiplied with the representation of frame B in A is actually the representation of C in A, right? So if C was a rigid body, then this is the same thing as saying how do you view C in A, is that you take the representation of C in B and you apply this transformation matrix on it, and that gives you the representation of C in A. And to get this transformation matrix, just represent the frame B in A. That makes sense, right? Awesome. Okay. So yeah, now you can understand how transformation matrices work, and this will be like handy when doing something like, I don't know, robotics. So if you have like multiple frames attached to your joints, so this is one frame, this is another frame over there, and maybe you have some other frame over here, and this is the final end effector, right? And if you want to figure out what's the position of end effector, knowing, you know, certain properties about these frames, right, you can of course figure out what the position of this thing is in this frame. But then how do you get this guy's position in that frame? That's through transformation matrices. You represent this frame in that, and then you multiply this guy's position by that transformation matrix, and you get in this frame. And then to get in that frame, you multiply by another transformation matrix, which is the representation of this frame in that frame. That makes sense? Okay. And that's how you get the position of end effector in the final frame. And yeah, that's why, you know, I mean, this is a handy tool, really. Okay. From here, things can get tricky. Just remember the context. We are talking about the transformation and rotation matrices that represent the frame B fixed to a body moving with linear and angular velocities, v vector and omega vector s on the frame S. a dot. Oh, so all of this is actually for, getting a formula. So getting a formula to represent our transformation matrix. Just as we did for the rotation matrix, we would also like to, get a formula to represent our transformation matrices, right? To calculate our transformation matrices. Yeah. So let's just, okay, I should actually probably tell you the thing. There is no formula. No, there's no general formula to represent the transformation matrix, but there is a very special case, uh, which is the screw motion. So for a screw motion, there is a formula with exponential, going on, and yeah, this thing. Once you read all of that, you'll understand that, yeah, okay. So for this case, you actually have a formula which you can get using e power, once again, some matrix theta, right? That's our transformation matrix, and there's the way to calculate it. This is slightly different from the form that we got for rotation matrix. You don't have this guy's powers. No, you don't have like, I plus sine theta times this matrix and then plus 1 minus cosine theta times this matrix squared. No, you don't have that. Instead, you have all of this. So it involves theta already. And yeah, just read through all of that. Oh, there's also all of this going on. So there's I should not be explaining this because it's not important. So there's twists and screws and whatnot, and you actually don't need all this. Really, you don't. So from here, everything is basically just the harder part and also the not so useful part, because this is used to represent screw motion only, and otherwise it's not actually all that useful. But yeah, once you have the screw motion, right, once you have the matrix for screw motion, now you can actually figure out how the motion actually was, like what was the angle by which you moved through on the screw, and all the other things, like what was the axis of the screw, what was the pitch for the screw motion, and other stuff. So yeah, I'll just stop here, because I don't think we'll be actually using all of that. I mean, at least you guys won't be using, or maybe you could be using, but then there are like better ways to do that. You could always, go through complex numbers or something like that. That's probably not the best way to be doing it in 3D though. In 3D, this is the best way, right? The formula that you will get, this is the best way to be representing screw motion in 3D. But when you have like a simpler case where there's only one frame in which you want to represent everything, go with something else. Go with complex numbers, maybe, right? So cylindrical coordinates, that's gonna help, right? Okay, so this is where I should stop, because all of this it's not important. It's really not important. So yeah, I'll see you guys next video. This was basically just to let you know that I'm still in the game, all right? I'm not just stopped studying. And yeah, I'll see you guys next video.